Hi everyone, and welcome to this my video on arrangements, part of the Mathematical Methods course here in Australia, and more particularly Mathematical Methods Units 1 and 2. But again, it really doesn't matter. This stuff is important worldwide. My name's Darren. Thank you very much for joining me. If you want to sort of watch all of the videos in this series, head to mathsguru.com, where basically there are these videos, downloadable lesson notes, VCAA exam questions, and so much more. And it's free to sign up. Wow, how exciting. Now, behind me is the learning objectives, and it's going to build on the previous video a little bit in just a moment. But it's going to understand what it means to be an arrangement, understand how to find the number of arrangements, and find the number of arrangements with and without restrictions. And again, this builds more and more as the videos of this series tend to go on. Now, as it's a new section of the methods course, there's nothing really I can recap. We're going to look at the number of ways we might be able to arrange a distinct number of objects. And the example I normally start with is imagine myself and two friends, i.e. three people, go to the cinema and there are only 3 seats available. How many different ways are there of the three of us sitting in those 3 seats? All right. And again, this is really the premise of what we're going to be dealing with. Now, before I go any further with this part of the video, if you can subscribe to my YouTube channel, that's massive. And it really does support the work I'm doing and makes me feel like I'm not sitting here talking to myself. And if you spread the word to your your mates and your teachers, if you find the videos useful, that would be massive as well. I want to help as many people as I can smash maths. Now, what is an arrangement? This is a number of different orders, a distinct number of objects can be placed. So as I say, 3 people, 3 seats. So an arrangement would be, one of those individual ways of sitting, as we'll come back to in a moment, all right? There may be a bit of a pattern to this, and I'm sort of going to show you now. Now, again, the wording of the question is really, really important. A lot of people trip up on the nuances here, but I tend to use lines, right? There are the 3 seats I'm going to sit on in the cinema. And again, remember, there are 3 people. So if I now look, again, going back to my stuff previously about the addition and multiplication rule, all right, I've got to work out how many people could sit in that initial first seat. Well, there were 3 of us. No one's sitting down at the moment. There are 3 different ways of doing it. And then, how many ways are there of sitting the second seat? Well, some people turn and go, well, there's 3. No, there isn't, because one of those has already been taken here. I, for example, have sat down. There's only my 2 friends left. So there must be 2 places, 2 people who I could choose to sit there. And again, it doesn't matter. I have absolutely no restrictions at this moment of time on who sits there. It's not like I've got to sit by my best friend. All right. Anyone can sit there because they're both my friends. All right. And again, how many people then are left here? Well, basically, there's only one person left there. And to go back to the video previously about the multiplication rule, because the first stage is sitting someone in the first seat, second stage, second seat, third stage, we're going to be doing multiplication rule for this. And when you multiply those together, you're in fact going to get 6 different ways. There are 6 different ways of 3 people to sit in 3 seats. And if you don't believe me, you can actually sit and do this with the letters if you call each of us A, B, and C. And then A, B, and C is going to be one of them. And A, C, and B could be another one. And B, A, C, and B, C, A, and C, A, B, and C, B, and A. And actually, those are the 6 different ways. Now, sometimes it actually helps to be able to write these things out, but most cases we're just interested in the number. How many ways there are arranging 4 different books on a shelf? Okay, well, 4 different books on a shelf. I'm just going to imagine that these books have little placeholders, and there's 1, 2, 3, and 4. Again, I've got 4 things to choose from initially. So there's my 4 things. So how many can I put in here? 4. I've used one of those choices. There must be 3 left here. I've used one of those choices. There must be 2 left here. I've used another one of those choices. There's only one way to fill a book there. And in which case, once again, because it's a choice, I'm going to do 4 times 3, which is 12, times 2, which is 24. And so in that situation, there are 24 different choices. Using this sort of box or line method actually makes life a lot simpler. Now, there is a rule to all of this, and obviously, hopefully, you're beginning to see this build up, that if there are, in fact, n objects arranged in a row, and there are n choices for the first position, there'll be n minus 1 choices for the second position, n minus 2 for the third, and it will keep going on until it gets down to 1. So what they're really saying is, if these were my choices, and again, I've got a variable number of choices, we knew that, I'm trying to change color, we knew that when I had 4 people, the first one there was going to be 4, right? That first box was 4 choices. So if I've got n choices, that one's going to be m. Then what did I do? Well, I took 1 away from whatever value was here, I took 1 away from. And then I took another one away, which is effectively n minus 2, and then minus 3. And we got all the way down to my last choice being 1. That's effectively what it's saying here. Right, so we're going to take all of those consecutive numbers from the highest number and multiply them all together until we get down to 1. So a photo is being taken of a group of 12 students. In how many ways are there of arranging the group so they all sit in a row? Okay, and again, I suppose what's important here is the idea they're sitting in a row. Right, let's get going. So we got 12 people in the first one, then 11, then 10, 9, 8, 7, oh sheesh, all the way down to 1. So I've now got to work out what 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 is. That's going to take a significant period of time on my calculator. So let's fire up my calculator and see how long this actually does take. Right, 12 times, oh, I'm not typing on the right one. 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 gives me, oh sheesh, how many numbers is that? 4, 1, 2, 3, 1, 2, 3, 479 million, 479 million, 1,600. Sheesh. Now, again, what if I had 20 books or 100 books? It would be crazy to assume that I've got to do this on my calculator. Wouldn't it be nice if there was, in fact, a shortcut? There is, and that's called factorial notation. Now, if I could have done, I'd have found the jokes on sort of YouTube or Instagram or TikTok that would have sort of talked about this factorial notation, lol. But basically, the notation, if we have a number and we want to multiply successive whole numbers all the way down to 1, then it's called a factorial notation. It is a factorial. So as I say here, 5 with an exclamation point, and that's what a factorial is the same as 5 times 4 times 3 times 2 times 1. So actually, bring up my calculator, I could have found this value much quicker by going, bear with me a moment, menu, algebra, I think, is it an algebra? It takes me a while to try and work out this one. Probability, there you go. It's in probability with a factorial. Now again, it said answer factorial. If I try and do that, if I try and do 479,000,1,600 times, my calculator will probably crack it. So let's do 12, and then we're going to go menu, probability, and factorial, and hit enter, and out comes the same value. Yay for the CAS. Can we use this now to help us? A painter is to paint the 5 circles of the Olympic flag. He cannot remember the colours to use for any of the circles, but he knows they should all be different. All right, so we've got 5 circles. He has 8 colours of paint available. In how many ways can he paint the circles on the flag? Now, this is a massive trick. You get so preconditioned to doing these questions, suddenly you're just going to do something silly like 5 factorial or 8 factorial, and that's not actually true. He's got 8 choices of colours, but actually only 5 circles. Right, so we're now starting to not use all of the choices that we have. And again, that is also important to pick up from these questions. So my first choice, I'm going to have 8 colors, then 7 colors, 6 colors, 5 colors, and 4 colors. Oh, now in that situation, I can't actually use factorial notation. Why? Because factorial would mean 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. All right, so in this situation, I would have to do 8 times 7 times 6 times 5 times 4, and that's my answer there, to give me the grand total of 6,720 different ways of effectively using those 8 colors in 5 different ways. Whoo! Is there a way, though, I could do this? Because again, what if I had 40 colors and 5 choices, or 40 colors and 18 choices? It would seem a bit silly to sort of do 40 times 39 times 38. Well, we love a good formula. And basically, the number of arrangements of n objects in groups of size r. So what we're saying is if we're not using all of the objects that we have and we're just grouping them into a much smaller number, we have the notation here as NPR. NPR. Now, an arrangement is also called a permutation, and that's actually where that P comes from. And you probably would notice if I bring my calculator up and go menu, probability, you'll notice here I've got permutation. So there is a function that can do this for me as well, but let's not rush ahead. Now that's given by n factorial divided by n minus r factorial. Again, not too interested in where that's come from. What we're saying is for the total number of things I can choose from, that goes on the top, and then the number of choices, or n factorial, n minus r factorial, is on the bottom. So going back to the example we had a moment ago, if I had, what was it, 8 colors and only 5 rings, then we would say that that would be 8 factorial divided by, well, 8 minus 5 gives me 3 factorial. And what was important when I went to school was understanding what this actually did. Because if we go back, what seemingly happened is the 3, the 2, and the 1, sorry, the next numbers there, 3 times 2 times 1, seem to have gone missing, all right? And again, 3 of those choices aren't being used. So 8 started with, 5 were actually being used, 3 of them not. So that would be the same as 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 3 times 2 times 1. And because of the way multiplication works, they cancel out, and I get my 8 times 7 times 6 times 5 times 4. Woo, lovely. All right, so let's look at another example. Find the number of different 4-digit numbers. All right, so we've got 4-digit numbers, 4 things, that can be formed from the digits 1, 2, 3, 4, 5, 6, 7, 8, 9. So my number of choices is 9. My groups are only 4. If each digit can only be used once. Okay, so if it can only be used once, and I'm not repeating, then I'm going to have NPR, which is going to be given by 9 factorial divided by 9 minus 4 factorial, which is 9 factorial divided by 5 factorial, which is going to give me 9 times 8 times 7 times 6. All right, and again, if I put that into my calculator, let's bring my TI Inspire up, and let's go back here, and we're just going to do 9 factorial. I'm going to work out one day if there is actually a shortcut for this, divided by, what did I say, 5 factorial, menu probability factorial, hit enter, gives me 3024 different choices. So 9 times 8 times 7 times 6 gives me 3024. Right, what about if the numbers can be used more than once? Now, in that situation, it's got nothing to do with factorials, really. It's got just down to common sense, because now if I've got 1, 2, 3, 4 digits, I've got 9 choices here. I've got the same 9 choices there, the same 9 choices there, and the same 9 choices there, which is 9 to the power of 4, which is 6,561. All right, so again, I love this box method. It makes it so much simpler, all right, to sort of work out what's going on. Now, what does it mean to be 0 factorial? All right, a lot of people turn around and go, oh, well, we know that if I have n objects, right, if I've got n objects, we know the number of ways of arranging that is given by n factorial, all right? So we know that n objects, n factorial. What if we had then the formula? We know that the formula got NPR is n factorial divided by n minus r factorial. Well, if we are going to arrange in group sizes equal to n, all right, so if I've got 4 objects and 4 spaces and 10 objects and 10 spaces, then what we're going to say in this situation is that n is equal to r. So this is now really going to be n p n, which gives us n factorial divided by n minus n factorial, or n factorial divided by, 0 factorial. But we know that this is the same. We know that n objects arranged in n different ways is the same as n factorial. So if that's got to be equal to n factorial, the only way that's going to be possible is if 0 factorial is actually equal to 1. That's one of those geeky things that I thought was quite cool. Now, here we go, arrangements with restrictions. Now we're going to start to build in some restrictions. How many different even 4-digit numbers? Now we've got even and 4 digits. There's really 2 restrictions there. Can be formed from the digits 1, 2, 3, 4, 5, 6, 7, and 8 if each digit can only be used once. That's important. Now, the best way to do this, I think, is to basically say, well, there's 1, 2, 3, and 4 different spaces. Now, I'm going to start looking at the restrictions first. I'm not going to start filling from here because that makes absolutely no sense, because they've told me that this last number here has to fall and be a specific one. Now, you're going to say, what do you mean? For it to be even, it's got to end in 0, 2, 4, 6, or 8. Now, before we go any further, that's got to be, and it's not actually going to be 5 choices. Why is it not going to be 5 choices? Because 0 doesn't actually appear in our list of given numbers, 1, 2, 3, 4, 5, 6, and 7, 8. So actually, I've got 4 numbers to choose from there. Right? So having chosen one of those numbers, out of the 8 numbers, I've only got 7 left. So that means we've got 7 numbers to choose from here, 6 numbers to choose from here, and 5 numbers to choose from here. So basically, multiplying those together gives me 840 different ways. Right? Again, the practice of this really does make you perfect. And I'm done. Thank you very much for watching. Have you enjoyed the video? If you have, if you can subscribe, that would be useful. If you found it useful, please let your friends and teachers know. That would be great as well. Right, did we understand what it means to be an arrangement? Yes, it's a permutation. It's one distinct order of a group of objects. Understand how to find the number of arrangements. Yes, we can use factorial methods, depending on whether it's restrictions or not. Find the number of arrangements with and without restrictions. I'm done. Thank you very much for watching. Hopefully, I'll see you in another video. Again, they're all found on mathsguru.com, free to sign up. If I don't see you again, I'm sorry. Was it that bad? That's okay. I get it. It's fine. Take care. I'll see you again. Bye-bye.